The story begins with a star in its final act, a brilliant performer on the cosmic stage reaching the end of its lifetime. For millions or even billions of years, it has burned hydrogen into helium, and then helium into heavier elements, sustaining itself through the delicate balance between the inward crush of gravity and the outward push of nuclear fusion. But eventually, that balance fails. In stars more massive than our Sun, the fuel chain progresses all the way to iron, an element that cannot release energy through fusion. At that moment, the core becomes a weight too heavy to support itself. Gravity takes control, and the star collapses. The collapse is catastrophic. In less than a single second, the core implodes, and its density skyrockets. Electrons are crushed into protons, forming neutrons, and the entire mass condenses into a sphere barely 20 kilometers across. Imagine taking a mass greater than that of our Sun and squeezing it into a city-sized object. A teaspoon of this material would outweigh mountains, pressing down with a mass of billions of tons. The outer layers of the star rebound off the compacted core, producing a titanic explosion that we see as a supernova. This explosion can briefly outshine entire galaxies, leaving behind either a black hole or something equally strange, but still visible: a neutron star. When the collapse halts just before the threshold of forming a black hole, the result is this bizarre neutron star. The pressure of degenerate neutrons resists gravity's inward pull, holding the structure in a tenuous balance. But it is a balance perched on a knife edge. The same star, with slightly more mass, would have fallen past the point of no return, disappearing into an event horizon. That is why astronomers often describe neutron stars as nature's balancing act, the last possible structure that resists collapse while still being visible to the universe. It is difficult to truly grasp the density of such an object. Our Sun has a diameter of about 1,400,000 kilometers. Yet, if you compressed it into a neutron star, it would fit inside the limits of a large city. Picture New York, Tokyo, or London. But instead of skyscrapers, imagine a sphere the size of the city containing a mass comparable to the star that sustains our entire solar system. This is no exaggeration, but the natural consequence of physics under unimaginable pressure. From a distance, a neutron star may seem unremarkable, a faint point of light lost among billions of others in the Milky Way. But as you approach, the nature of its surface becomes horrifying. Gravity is more than 200 billion times stronger than what we feel on Earth. If you were to stand on the surface, which is impossible for any human body, a fall from a single centimeter would smash you into subatomic debris before you reach the ground. Yet within this crushing environment, light itself still manages to escape, though not without a struggle. Neutron stars are on the razor's edge of physics. Their cores contain exotic states of matter that we cannot reproduce in laboratories on Earth. Some theories suggest layers of neutron-rich nuclei, seas of free neutrons, and perhaps even more exotic phases, like hyperons or quark matter deeper inside. The exact structure remains uncertain, because at densities many times greater than an atomic nucleus, the usual laws of matter break down. But no matter the details, the overarching truth remains the same. This is the closest nature can come to creating a black hole without crossing the final boundary. The distinction between neutron star and black hole is subtle but decisive. In both cases, gravity dominates to an extraordinary degree. But in a neutron star, the escape velocity at the surface is less than the speed of light, which means photons can still struggle upward. In a black hole, that velocity surpasses light itself, trapping all information forever. Thus, the neutron star stands as the last bastion, the ultimate heavy weight of the cosmos that still permits light to flee into the night sky. When astronomers detect these objects, they are not simply observing stars in decline. They are watching physics itself, pushed to the absolute limit. A neutron star is like a frozen scream from a collapsing giant, a reminder of how gravity, matter, and light interact in ways both violent and beautiful. The core that once fueled fusion now serves as an extreme beacon of relativity and quantum mechanics colliding in a single place. Each photon that leaves the surface carries a story of survival, of climbing out from a prison of gravity that nearly rivaled a black hole. The edge of possibility is where neutron stars reside. They are cosmic tightrope walkers, balancing between continued existence and total collapse. From the viewpoint of the universe, they are relics, remnants of stars that once illuminated galaxies. To scientists, they are laboratories of extremes, offering insights into conditions that no particle accelerator could hope to achieve. To storytellers, they are symbols of defiance, places where even under the heaviest weight imaginable, light still breaks free. And so we end this first approach with a haunting transition. Imagine the crushing weight, the star's core shrinking into 20 kilometers of relentless matter, and light trembling at the edge of escape. This is gravity at its most merciless, bending time and space almost to the breaking point. And yet, it is not enough to silence light forever. The question becomes, how strong is the gravity, and how does light manage to endure? That is the journey we take next. The collapse of a massive star does not happen gradually in the way that mountains erode or rivers carve valleys over thousands of years. It happens in an instant, as though the universe flips a switch. At the very moment when fusion no longer provides pressure to resist gravity, the core plummets inward, faster than thought, faster than any human sense of speed can comprehend. The iron core of the star, perhaps larger than the Earth itself, contracts to a fraction of its size in less than a heartbeat. In this implosion, particles that once orbited in ordered shells are thrown together with such force that they merge. Protons and electrons, normally kept apart by electric repulsion, are squeezed into neutrons. What remains is matter stripped of nearly everything that once made it familiar. A sea of neutrons packed as tightly as the laws of physics will allow. In this incomprehensible environment, the rules of quantum mechanics come to the rescue. The neutrons obey what physicists call degeneracy pressure, a principle that no two identical particles can occupy the same state at the same time. This invisible rule is the final line of defense that holds the star against collapse. Without it, the star would fall straight into a black hole and vanish. But with it, the neutron star stabilizes into a dense, city-sized remnant that endures for millions or billions of years, slowly cooling as it radiates its trapped heat into space. For the outside observer, this object is almost beyond imagination. If you could place a single sugar cube of neutron star material on Earth, it would weigh more than a mountain range. The gravity binding it is so intense that it bends not only the matter around it but also the very fabric of space and time. The surface gravity is hundreds of billions of times stronger than what humans experience at sea level. Even though Einstein's equations predict such conditions with mathematical precision, describing them in words feels like trying to bottle a storm in a glass. Yet despite the monstrous strength of gravity, a neutron star is not a black hole. That difference is everything. For the neutron star, the boundary has not yet been crossed. Light can still rise from its surface. Photons born in the furnace of the crust, or in magnetic storms above it, can climb into space, though each one must fight through an energy well deeper than anything else in the universe except a black hole. Each photon that escapes is a survivor, proof that this is still a visible object, still part of the universe we can observe. Astronomers often speak of neutron stars as natural laboratories, but they are more than that. They are thresholds. They mark the dividing line between existence that can be known and existence that is forever hidden. A neutron star is like the last fortress before the abyss. Its walls of matter press so tightly that even the nuclei of atoms cannot exist in their ordinary form. The crust of the star may still contain some exotic nuclei, but beneath that crust lies a sea of neutrons flowing like a quantum liquid. Below even that, the core may hold phases of matter that have no name in earthly science, perhaps particles heavier than neutrons, perhaps quarks liberated from their prison inside nucleons. We cannot say for certain. All we know is that nature permits such states for a moment, and light escaping from the surface carries whispers of what lies within. When we gaze at a neutron star, we are not just seeing the remnant of a supernova. We are peering at the razor's edge of reality. One step more massive, and the object would be a black hole, shrouded forever by an event horizon. One step less massive, and it would not have collapsed at all, remaining a white dwarf, a pale ember slowly fading. Neutron stars are the middle path, rare and fleeting, the exact point at which matter resists gravity's final demand without surrendering completely. They are like cosmic riddles, challenging us to understand how light can flee from such crushing depths. the energy of the explosion that births them is also worth lingering on. A supernova releases more energy in a few seconds than our sun will emit in its entire lifetime. That energy radiates across space, sometimes visible even in the daytime sky of Earth. As it was when Chinese astronomers recorded the supernova that created the Crab Nebula in the year 1054. At the heart of that nebula lies a neutron star, spinning 30 times per second, its beams sweeping across the cosmos, like the rotating lamp of a lighthouse. That pulse of light, repeating with perfect regularity for centuries, is the testimony of a neutron star's survival. Light escaped then, and it escapes still, a proof against gravity's attempt to silence it. In the end, what makes neutron stars so compelling is not only their density or their violence, but the paradox they embody. They are places where gravity has almost won, but not entirely. Where light should be extinguished, it instead struggles free. Where matter should vanish beyond an event horizon, it remains visible, if only as a faint ember glowing against the night sky. To study neutron stars is to study resistance itself, the resistance of quantum laws against collapse, the resistance of light against gravity, the resistance of the universe to total silence. And as we close this second part of the journey, imagine standing near such an object. Though, in reality, no human body could survive the approach. Imagine the warped horizon where the curvature of space bends your vision, where the surface of the star appears distorted, where even time itself slows relative to your heartbeat. In that environment, you would feel gravity pressing on you with unbearable force, and yet you would see light streaming upward, a reminder that even here, escape is possible. But escape is not simple, for the light that does emerge carries scars of its struggle, stretched in wavelength, red-shifted by the climb, bent by curvature, and twisted by the gravity it defied. To understand that journey, we must next explore the exact strength of this gravity, and why only light itself can endure it. To truly feel the weight of a neutron star, imagine holding the Earth in your hand. Now compress that sphere until it fits into a sphere only a few tens of kilometers across. The same mass is there, the same gravity, but it has been forced into a volume so small that the density defies imagination. Every cubic centimeter of the star contains more matter than entire mountains on Earth. The pressure is so intense that no atom remains intact. Electrons are forced into protons, leaving behind a sea of neutrons, each one pressed against the next, a lattice of matter that is more like a single colossal nucleus than anything familiar. The moment of formation is violent, yet the result is strangely stable. The explosion of the supernova expels the outer layers into space, creating glowing nebulae that shine for centuries. The remnant core, however, does not expand again. It remains locked in its compact form, spinning with furious speed, and often carrying a magnetic field trillions of times stronger than that of Earth. This field can twist and shape the radiation escaping from the surface, sculpting beams that sweep through space like rotating searchlights. But even without those beams, the surface itself is a paradox. It radiates immense energy, and still, it holds that energy against a gravity so strong that every photon must claw its way outward, climbing a steep slope in the geometry of space and time. The balance that keeps a neutron star from collapsing into a black hole is a knife edge of physics. Add too much mass, and the degeneracy pressure of neutrons can no longer resist gravity. The star crosses the boundary, collapsing into a singularity hidden by an event horizon. Remove mass, and the collapse would not have gone so far. What remains instead is a white dwarf, glowing softly but nowhere near the crushing density of a neutron star. Between these two extremes lies the narrow band where neutron stars exist, a state so fragile that it is remarkable nature produces them at all. Light itself is the testimony of their existence. Unlike black holes, which reveal themselves only through indirect effects, like the distortion of nearby matter or the release of energy from accretion disks, neutron stars shine. Their photons reach us, battered and altered, but still present. They remind us that gravity has not yet won. When astronomers detect the faint pulses from a neutron star thousands of light years away, they are not merely observing radiation. They are hearing the echoes of a battle between matter and gravity, a battle in which light manages to escape even when every force seems stacked against it. The scale of these objects forces us to question our usual sense of size and proportion. On Earth, we think of mountains as enormous and rivers as endless. In the cosmic theater, those measures shrink to nothing. A neutron star, only 20 kilometers across, outweighs entire clusters of planets. Its spin can be so rapid that it rotates hundreds of times each second, faster than a kitchen blender, and yet with more inertia than a billion Earths. Its magnetic field is strong enough to rip apart atoms at great distances, stretching them into filaments. This is not just another kind of star, it is a different category of being, one that bends the very rules of physics into new shapes. And yet, despite their strangeness, neutron stars remain among the most studied objects in astrophysics. They are nearby enough in cosmic terms for our telescopes to observe them directly. They are luminous enough to cut through the background of the galaxy. They are common enough that hundreds are catalogued, with many more waiting to be found. Each one is unique, carrying the imprint of its birth mass, its spin, its magnetic field, and its environment. Together, they form a population that teaches us not just about their own nature, but about the fate of massive stars and the workings of matter under the most extreme pressures. But there is something more than data in their light. There is a kind of defiance. The neutron star should not exist. Gravity should have crushed it beyond recognition. Yet because of quantum mechanics, because of the stubborn refusal of neutrons to share the same state, it remains. And in that persistence, light finds a way to flee, climbing against the weight of 200 billion times Earth's gravity to scatter across the galaxy. Each ray that reaches our instruments is a message written in survival. So as we conclude this opening chapter, picture again the sequence. A massive star burns for millions of years. Its fuel is spent. The core collapses. A supernova tears through the cosmos, leaving behind a sphere of neutrons no wider than a city. That sphere spins, glows, and warps the very space around it. Its gravity is so strong that light trembles at the edge of escape, yet it still manages to rise. This is the neutron star, a cosmic heavyweight perched on the razor's edge between existence and oblivion. Its story is one of collapse, survival, and resistance, and it sets the stage for the deeper mystery we now face. For if light does escape, how exactly does it manage? How can photons find their way through a gravity well so profound that even time itself slows to a crawl? That question leads us onward, into the heart of the next chapter, where we will explore the raw strength of this gravity and the fragile triumph of the light that defies it. To stand on the surface of a neutron star, if such a thing were possible, would be to experience gravity at its most merciless. On Earth, gravity tethers us gently, holding oceans against the crust and anchoring us as we walk. On the neutron star, gravity is no longer a background force. It is the ruling presence, the first and final fact of existence. It presses downward with a strength beyond comprehension, more than 200 billion times greater than the pull we feel on our planet. That means that a fall of a single centimeter on the neutron star would not merely bruise or break bones, it would obliterate matter, smashing atoms into subatomic fragments, tearing apart any structure that tried to resist. This surface gravity is so powerful that even imagination struggles to keep up. Consider the escape velocity, the speed needed for any particle or object to climb away from the gravitational grip. On Earth, that velocity is about 11 kilometers per second, fast enough that rockets must burn for minutes to achieve orbit. On a neutron star, the escape velocity reaches nearly half the speed of light, about 120,000 kilometers per second. Nothing with mass could ever hope to launch itself into space from such a surface. Even if we could imagine a rocket with infinite fuel, the structure of the rocket would collapse under its own weight long before it left the ground. And yet, light does manage to flee. Photons, massless packets of energy, travel at the cosmic speed limit, the speed of light itself. That speed is the one thing gravity cannot slow. Gravity can bend light, it can stretch its wavelength, it can trap it if the escape velocity equals or exceeds the speed of light, as in a black hole. But on a neutron star, the escape velocity, while staggering, remains just short of that ultimate limit. So photons born on the surface or in the magnetic storms above it can still climb out, though each one must sacrifice part of its energy along the way. Einstein's theory of general relativity gives us the language to describe this ordeal. In that theory, gravity is not a force in the ordinary sense, but a warping of the geometry of space and time. The neutron star curves the space around it so steeply that even light, which has no mass, must follow a twisted path. From the perspective of the photon, it is always traveling straight, always moving at the same speed. From the perspective of the universe, that path is bent, and the energy of the photon is drained as it ascends. The numbers are merciless. Imagine trying to throw a stone from the surface of the neutron star. To escape, it would need to move at nearly half the speed of light. That is tens of thousands of times faster than any projectile ever launched by human hands. Even subatomic particles with mass, like protons or electrons, cannot reach such speeds from a resting state on the surface. They remain bound, trapped forever in the grip of the star. Only the massless photon, born already traveling at the speed of light, can carry news of the neutron star to the outside universe. But this freedom is not without cost. Light, leaving the surface of a neutron star, emerges redshifted, its frequency lowered by the struggle against gravity. X-rays and gamma rays emitted by the hot surface are stretched into longer wavelengths as they climb. By the time they reach our telescopes, they carry the scar of the battle they endured, encoded in their color. In this way, the strength of gravity does not only hold matter in place, it imprints itself directly onto the radiation that escapes. To appreciate the enormity of this gravitational pull, compare it to the black hole. In a black hole, the escape velocity at the event horizon equals the speed of light. No photon, no matter how energetic, can escape once it is born within that horizon. A neutron star hovers just shy of that threshold. Its surface is like the edge of a waterfall, where the water still manages to spray upward even as the current plunges into the abyss. Light can climb, but the margin is slim, and the journey is punishing. Astronomers measure this strength not with rockets or stones, but with the very light that escapes. By studying the redshift of spectral lines, they can calculate how deep the gravity well must be. Each shift in frequency is a direct signature of the gravitational field. This is not speculation, but observation, confirmed across decades of data. The measurements reveal a gravity so extreme that even time itself runs slower near the surface. A clock placed on a neutron star would tick more slowly than one far away in space. This time, dilation is not illusion, but reality, another consequence of the geometry carved by gravity. For us, the conclusion is stark. The neutron star represents a world where only light can truly escape. Matter remains bound. Sound, motion, and objects all collapse under the weight of gravity. Only the photon, traveling at the universal limit, survives the climb. But even that survival comes with a cost, as the next part of this journey will show. To escape does not mean to remain unchanged. Light that emerges from a neutron star carries the memory of its battle, written in redshift, in bending, in distortion. It tells us not only that it survived, but also how strong the gravity was that nearly claimed it. To measure gravity in everyday life, we drop a ball, we watch it fall, and we time its descent. On Earth, the acceleration is gentle, about 10 meters per second each second. You can see it, feel it, but you can resist it with a jump or a strong lift. Now magnify that by 200 billion. On a neutron star, a ball dropped from your hand would strike the surface not with a thud, but with an annihilation. The atoms of the ball would disintegrate under the crushing acceleration before they even touched the ground. That is how severe gravity is on these stars. It does not merely pull, it unravels the very fabric of matter. The escape velocity is another way to frame this strength. On Earth, 11 kilometers per second is enough to leave our planet behind. On Jupiter, the giant of our solar system, it takes 60 kilometers per second. These are speeds we can imagine, even if we cannot achieve them with ease. On a neutron star, the number is nearly half the speed of light, more than 100,000 kilometers per second. That is not a speed one can imagine in the context of rockets or spaceflight. It is a speed that belongs to photons alone. The strange part is that escape velocity is not just about speed. It is about the nature of space-time itself. In Einstein's theory, gravity bends space and slows time. Clocks near a neutron star tick more slowly than clocks in open space. Distances shrink and stretch in ways that defy ordinary geometry. When we say that the escape velocity is 40% of the speed of light, what we mean is that the fabric of space-time is so steeply curved that only the most fundamental traveler of the cosmos, light itself, it can rise from that pit. Everything else is bound. Even light, however, is not untouched. As it climbs, it loses energy. Imagine a runner sprinting uphill, muscles burning. Each step, a battle against gravity. For the photon, there is no slowing down, but there is a stretching of wavelength. The photon begins its journey as an energetic X-ray, but by the time it reaches distant space, its wavelength has lengthened, its energy diminished. This gravitational redshift is the mark of the climb. It is the toll gravity demands from every escaping traveler. Scientists have confirmed this redshift by observing neutron stars directly. Spectral lines from atoms on their surfaces appear shifted, stretched to longer wavelengths. The degree of the shift tells us how strong the gravity is, how deep the well that the light has climbed out of. These observations match the predictions of general relativity with precision, proving that the crushing gravity is not only theory, but an observable reality. It is easy to think of gravity as a force pulling down, but that image fails in such extreme places. Better to think of it as a landscape. The neutron star creates a valley in space-time, a pit so deep that even light must struggle to escape. From a distance, we see the photons emerge. But if you stood at the surface, you would know that each one carries the cost of the climb, each one thinned and stretched by the journey. This gravity also shapes the way we see the star. Light emitted from the far side of the neutron star can be bent by gravity so that it curves around and reaches us. That means we can see more than half the surface at once, as though the star were turning itself inside out. It is a distortion, not of the star itself, but of the space around it. This bending is a reminder that gravity does not merely hold objects. It bends vision, it bends the path of light, and it bends time itself. No human experience on Earth can match this. Even the strongest gravitational field we know firsthand, the pull of Jupiter, is nothing by comparison. A neutron star is not an exaggeration of gravity, but a transformation of it. The familiar becomes strange, the possible becomes impossible, and yet photons still find a path out. That fact is astonishing. If the star were only slightly more massive, the escape velocity would equal the speed of light, and no photon could leave. That is the black hole's domain. The neutron star exists in the narrow band just before that threshold, the last visible object before the universe's event horizons begin. The strength of this gravity challenges not only matter but imagination. We build metaphors to describe it, comparing it to mountains, oceans, and explosions, but none of these images suffice. Only the equations capture it precisely, and even then, the equations themselves strain the limits of comprehension. What matters is that light still finds a way, and that we, from across the galaxy, can intercept that light and decode its message. As we look closer at the light that escapes, we will see not only bending and redshift, but also warping, splitting, and twisting, signs of gravity's grip on every photon. To escape is only the first step. To arrive unchanged is impossible. And that leads us to the next revelation, that light is not merely slowed by gravity, but reshaped by it, carrying the fingerprint of the star in every wavelength. When we speak of gravity on a neutron star, we are not only describing a pull, but the reshaping of the universe itself. Space is drawn inward, time is slowed, and the surface becomes a place where nothing familiar survives. A mountain would collapse in an instant, an atom would be crushed beyond recognition. Even the core of an iron block, the strongest of ordinary materials, would fail to withstand the pressure. Matter here is not matter as we know it. It is stripped down to neutrons packed like grains of sand in an infinite desert, each touching the next without space between. And yet, the neutron star does not crush itself entirely. The reason is subtle but profound. The Pauli exclusion principle, a quiet law of quantum mechanics, forbids neutrons from all sharing the same state. This resistance is tiny in ordinary circumstances, invisible in daily life. But under the pressure of a collapsing star, it becomes a wall strong enough to resist gravity itself. In this way, The smallest of rules balances against the mightiest of forces, holding the star in existence. Without that principle, there would be no neutron stars, only black holes swallowing everything without trace. Still, the equilibrium is fragile. Add just a little more mass, and the pressure cannot resist. The star collapses further, the escape velocity crosses the ultimate boundary, and light itself is lost. This is why neutron stars are said to balance on the razor's edge. They are cosmic survivors, caught between the visible and the invisible, between stars that shine and black holes that hide. What does this mean for the light that escapes? It means that every photon is evidence of that balance. Born in fire or magnetism at the surface, the photon begins its journey upward. The gravity well is deep, and the climb is steep. The photon cannot slow, for it always moves at light speed, but it can stretch. Its wavelength lengthens as it trades energy for distance. The redshift is the price it pays to reach us. By the time it arrives at our telescopes, the photon is dimmer, its color shifted. But it is there, proof that escape is possible. Astronomers calculate the strength of this redshift with precision. They use it as a probe of gravity, as a measure of the star's mass and radius. These measurements confirm what theory predicts. The gravity at the surface of a neutron star is 200 billion times Earth's. The escape velocity is nearly half the speed of light. Time runs slower, space curves sharply, and yet photons emerge. If there were any less clarity, one might doubt such extremes. But the evidence is there, written in light itself. Think of this. If you stood near the neutron star, which is impossible, and you watched a distant galaxy, its light would appear blue shifted, brighter, and more energetic, because you would be deep inside the gravity well. But to the distant observer, watching light leave the neutron star, the opposite occurs. The light stretches, reddens, weakens. This symmetry is the beauty of relativity, showing that what we see depends entirely on where we stand in the geometry of space-time. And so we return to the core truth. Only light can escape the neutron star. Nothing with mass, no object or person or machine could ever rise from its surface. Only photons, carrying no rest mass, can climb out, though even they are altered by the struggle. In this way, the neutron star is not only a remnant of a supernova, it is a stage on which the laws of physics reveal themselves in purest form. Gravity, quantum mechanics, and relativity all meet here, clashing and balancing in ways that decide whether light survives. From Earth, we are distant witnesses. The light travels across thousands of years, through interstellar clouds and the emptiness between stars, to reach our telescopes. When it does, it tells us a story of survival. It tells us that gravity was almost victorious, but not quite. It tells us that even in the most crushing environments short of a black hole, there is still escape. And it tells us that the universe itself is capable of extremes that test every law we know. As Chapter 2 draws to its close, imagine once more the surface of the neutron star. Picture the gravity pressing so hard that space folds inward, that time slows, that matter is forced into states we cannot name. Now picture a single photon, a quanta of light, born in that pressure. It surges upward, bends along the warped geometry, loses its energy, but it rises still. Against odds that seem absolute, it reaches the open universe. That photon, faint but undefeated, carries the voice of the neutron star across the cosmos. And here the question sharpens. If light does escape, what form does it take when it arrives? How does gravity change it, twist it, and leave its mark upon it? To answer this, we must follow the photon more closely. We must see how gravity inscribes its presence into the color and energy of the light, leaving a redshift that cannot be erased. That is the path forward into the next chapter, where we will trace the scars left on light by its journey out of the deepest gravitational wells. When light flees the surface of a neutron star, it does not escape unscathed. The journey upward through the crushing gravity is not like a rocket rising through the thin layers of Earth's atmosphere. It is more like a swimmer trying to climb a waterfall, straining against a current that never weakens. The photon cannot slow down, for the speed of light is absolute, but it can surrender some of its energy to gravity. And in the language of physics, to lose energy means to stretch in wavelength. to shift from higher frequencies to lower ones. This is the phenomenon we call gravitational redshift. Imagine the surface of a neutron star glowing with searing heat. The crust may reach millions of degrees, producing radiation in the form of X-rays and gamma rays. These are photons of extraordinary energy, waves with frequencies so high they can pass through lead and stone with ease. But as they attempt to rise, they must climb out of the gravity well that is more than 200 billion times deeper than Earth's. Each photon spends energy in the climb, and as it reaches free space, its frequency has decreased. X-rays are shifted towards softer bands. Gamma rays are stretched toward X-rays, and even visible light would be reddened. To us, observing from across the galaxy, the star's true color is always shifted downward, always tinted by the scar of its gravity. This is not a trick of perspective, nor an illusion of speed, but a fundamental change in the photon's nature. Einstein first described it as a consequence of general relativity, the same theory that predicted the bending of starlight around the sun during an eclipse. In relativity, energy and time are intertwined. A photon's frequency corresponds directly to its energy. As time runs more slowly in the strong gravity near the neutron star, the photon's oscillations also slow relative to a distant observer. The redshift we measure is time dilation made visible, a direct sign that time itself flows differently near the star. The effect can be described in equations, but the reality is more visceral when you imagine it. Suppose a nuclear reaction on the surface produces a sharp line of radiation at a specific frequency, like a bell ringing at a perfect pitch. By the time that radiation reaches Earth, the bell's tone has lowered, the pitch has deepened, the sound has been stretched. No matter how carefully you tune your detector, you will find the note has shifted. This is gravity's handwriting, inscribed on the light itself. Astronomers have looked for this effect in the spectra of neutron stars for decades. With X-ray telescopes like Chandra and XMM Newton, they examine bursts and surface emissions, searching for lines that appear at lower frequencies than they should. The results confirm the prediction. Photons leave the neutron star altered. Their frequencies are not those of free space, but of a battle against gravity. Every observation strengthens the case that the equations of relativity are not abstract, but lived realities for the photons we detect. The gravitational redshift is not unique to neutron stars. It occurs near all massive objects, even on Earth. Light climbing from our planet's surface is redshifted ever so slightly, but the effect is so minuscule here that it requires atomic clocks to detect. On a neutron star, the effect is colossal, plain to see, impossible to ignore. The difference is one of scale, the same laws written in bolder letters. What is subtle on Earth becomes overwhelming at the surface of a neutron star. Think for a moment about what this means. If we could somehow see the neutron star's surface directly, with no intervening effects, it would appear hotter, brighter, and more energetic than we actually observe. But we can never see it that way, because the light that reaches us has been transformed in the climb. In a sense, we never see the star as it is, only as gravity allows it to be seen. We see not the true face, but the face filtered through warping space-time. For astrophysicists, this fact is both a challenge and a gift. It means we cannot take observations at face value. We must always account for redshift when estimating temperature, luminosity, and energy. But it also means we can use the redshift as a tool. The amount of shift tells us how deep the gravity well is, and therefore how massive and compact the star must be. In this way, light carries not only an image of the star, but also a measurement of its gravity. The star may be unreachable, but its photons deliver its secrets across the gulf of space. The redshift is more than physics. It is also symbolism. Light is born at the surface full of energy, blazing with power. Yet as it rises, that power is drained. By the time it reaches us, it is weakened but not destroyed. It is stretched, altered, marked by the battle, but it still arrives. In that story of survival, one can see a metaphor for endurance itself. The persistence of signal against overwhelming odds. The universe writes poetry in the way photons struggle through the grip of gravity. And as we close this first part of the chapter, we prepare to look even closer. If light is redshifted, then every photon is a messenger, not only of the star's surface, but of the gravity it escaped. What else does this message tell us? How precise are these shifts? And what can we deduce about the structure of neutron stars by studying them? To follow that trail, we must dive deeper into both theory and observation, tracing the ways astronomers read these faint signatures to unlock the interiors of stars that otherwise remain hidden. The concept of gravitational redshift may appear abstract, but its reality becomes vivid once we follow a single photon's journey. Imagine a photon born on the neutron star's surface in the chaos of nuclear reactions and magnetic storms. At the instant of its birth, its wavelength is short, its energy immense, belonging to the domain of X-rays or even gamma rays. For a moment, it is pure fire, the sharp edge of the spectrum. Then the climb begins. The photon moves outward, always at the same speed. But in a universe where speed alone is not the full measure of motion, it is climbing against the slope of curved spacetime. This slope does not slow the photon's pace, but it exacts a different toll: energy. Step by step, the wavelength lengthens, the frequency drops. To us, far away, the photon has been redshifted. What was once a gamma ray may reach us softened into an X-ray. What was once an X-ray may arrive as a faint trace on the edge of our detectors. This effect is inseparable from time itself. Near the neutron star, time runs slower. If you could hover above the surface with a clock, each tick would take longer relative to a clock far away. To a distant observer, the photon's oscillations are stretched in the same way. What was one cycle per moment near the star becomes fewer cycles per moment when viewed from afar. The photon has not changed its speed, but the very rhythm of time has altered the way its frequency is perceived. To picture this, think of a singer on a stage at the bottom of a canyon. As the sound waves rise, they lose energy, their pitch lowered by the climb. By the time the music reaches the listener on the rim, it has changed tone, softened by the distance and the slope. Light leaving a neutron star is like that, except that the canyon is not rock, but space-time itself. This stretching is more than a curiosity, it is measurable. Observations of neutron stars show emission lines shifted by amounts consistent with gravitational redshift. For example, when astronomers study X-ray bursts from accreting neutron stars, they find the spectral features displaced, the fingerprints of atoms stretched in wavelength. These displacements are not errors. They are the scars of the photon's journey. They reveal the mass and radius of the star, encoded in the very light that escapes. The most dramatic evidence comes from pulsars, neutron stars that sweep beams of radiation across space with clock-like precision. When their beams reach us, the timing and frequency can be compared with models of their rotation and emission. The differences confirm that gravity has shifted the light. The pulses are not only lighthouses across the galaxy, they are clocks, and their ticks reveal how strongly gravity slows time and stretches energy. What makes this remarkable is that the photons do not lose energy into nothingness. They give it to gravity itself. In relativity, energy is not a substance that leaks away. It is a relationship between observer and space-time. To the photon itself, nothing has changed. To us, far away, the climb is visible as redshift. The difference lies not in the photon, but in the geometry of the universe between where it was born and where it was seen. For astrophysicists, this provides a direct probe of conditions that cannot be reached in laboratories. No collider on Earth can reproduce densities billions of times greater than an atomic nucleus. But neutron stars do, and their light carries the record of those conditions. Each redshifted photon is like a sample jar brought back from a forbidden place, proof of what happens when matter and gravity collide at their limits. The poetry of this is difficult to ignore. Light, the swiftest traveler, is slowed not in speed, but in song. Its voice is pitched lower, its color shifted, as though gravity itself has taken hold of the note and bent it. To see a neutron star is to hear that altered music, the tones deepened by the star's weight. It is as if the cosmos itself has an organ tuned to the chords of relativity, and neutron stars are the pipes through which it plays. And so, as we prepare to continue, we carry this insight. Gravitational redshift is not an illusion, but a fact, a signature, carved into light. It proves that time is slower near a neutron star, that energy is drained in the climb, that photons survive but not unchanged. In the next part, we will follow this insight further, exploring how astronomers read these redshifts like hieroglyphs, translating them into the story of the star's density, its mass, and its very structure. Light is the messenger, but gravity is the author of the message. The photons that reach us from a neutron star are weary travelers. They are survivors of a climb so steep that even space itself seems to collapse inward. By the time they arrive, they are altered. Their frequencies have shifted downward, their colors softened, their energies diminished. But hidden within those changes is a map of the gravity that shaped them. Astronomers read these redshifts as one would read the bends in a river, tracing them back to the landscape that formed their path. To understand how this works, imagine a neutron star with a specific mass and radius. The depth of its gravity well depends on those numbers. A more massive star produces a deeper well. A smaller radius makes the slope steeper. The photons climbing out pay a heavier toll in redshift if the star is more compact. By measuring the exact amount of shift, astronomers can calculate the ratio of mass to radius. This is no small achievement. It allows us to weigh an object we cannot touch and measure its size when it is smaller than a single city and thousands of light years away. One famous case is the neutron star at the heart of the system known as XO 0748-676. Observations of its X-ray bursts revealed absorption lines shifted by amounts consistent with strong gravitational redshift. The data suggested a compact object with mass near that of our Sun, but packed into a radius of only about 10 kilometers. These measurements confirmed that light leaving the star had been stretched by gravity to a degree predicted precisely by general relativity. In this way, photons carried not just their own story, but the dimensions of the star itself. The precision of this tool is what makes it invaluable. Each shift is a clue, each spectral line a fingerprint. When telescopes like Chandra, NISA, or XMM Newton collect data, they are not simply gathering images. They are listening to light's testimony, parsing the subtle changes imprinted by the climb. With these clues, scientists can infer whether the core of the star contains only neutrons or whether stranger states of matter lurk inside. Hyperons, quarks, or exotic condensates may all leave their mark indirectly by shaping the mass and radius, which in turn shape the redshift of light. Beyond the measurements, there is something haunting about the idea that gravity leaves its mark on every photon. It is as if the star itself brands its light, stamping it with proof of the struggle. No photon emerges pure. All carry the signature of the pit they escaped. This means that every neutron star is, in a sense, speaking to us, telling us the depth of its gravity well through the colors of its light. It is a cosmic dialect, a language of redshift, one we are just beginning to master. The story of gravitational redshift is also a story of validation. When Einstein first predicted the effect, it was considered nearly impossible to confirm. The shift on Earth was too small to see. But the universe provided its own laboratories. White dwarfs showed small shifts. Neutron stars revealed enormous ones. What began as a theoretical consequence of equations became a measured reality, confirmed again and again by photons crossing the gulf of space. Think of light as a messenger climbing out of a dungeon. It cannot change its speed, but it can lose strength. By the time it emerges into freedom, it is altered, marked, and weakened. But the fact that it emerges at all is testimony to its resilience. For every photon we detect from a neutron star, countless others remain bound, absorbed, or scattered inside. The ones we see are the victors of an unseen struggle, their voices deepened by the climb. And so the chapter draws to a close. We began with the idea that light can escape a neutron star's crushing gravity. Now we see that to escape is not to emerge untouched. The photons carry evidence of the ordeal, redshifted by the depth of the well. This redshift is both a wound and a gift. It marks the cost of survival, but it also gives us knowledge of the star's mass, radius, and structure. Without it, we would know far less about the hearts of these collapsed giants. As we move onward, the journey of light does not grow easier. Escaping gravity means more than just stretching in wavelength. It means bending, warping, and curving along paths that defy straight lines. The neutron star's field is so intense that light itself bends back toward it. allowing us to see parts of the surface hidden from view. In the next chapter, we follow this bending more closely, tracing how gravity distorts vision and reveals more than half the star at once, turning light into a twisted echo of its origin. When photons leave the surface of a neutron star, they do not travel outward in straight lines. The crushing gravity curves the space around the star so steeply that light itself must bend. This bending is not a trick of perception, not an optical illusion, but the real path that photons follow in warped spacetime. The result is strange and haunting. From our vantage point, we can see more of the neutron star's surface than should be possible. Light from the far side curves around the star and reaches us, so the star shows more than half of its face at once. To understand this, recall that Einstein's theory of general relativity replaced Newton's idea of gravity as a force with a new image. Mass tells spacetime how to curve, and spacetime tells objects how to move. For light, which has no mass, the rule still applies. A photon always moves in a straight line, but what straight means depends on the geometry of spacetime. Near a neutron star, the geometry is curved inward. To us, looking from far away, the photon's path appears bent, as if it were deflected by an invisible hand. On Earth, we can see this effect in gentle form. During a solar eclipse, stars behind the sun appear displaced, their light bent by the sun's gravity. The amount of bending is small, but measurable, and it was this very observation in 1919 that confirmed Einstein's theory to the world. On a neutron star, the effect is magnified beyond imagination. The gravity is billions of times stronger than the sun's. The bending is so severe that photons launched nearly sideways can still curve upward and escape. To an observer at a distance, this means the neutron star's outline is swollen and distorted, a glowing sphere that shows not half but nearly 3/4 of its surface at once. This warping challenges our sense of vision. Normally, to see an object, you must face it directly. But around a neutron star, photons from the hidden hemisphere wrap around the curve of spacetime and reach you. The star shows you what should be invisible. It is as if the rules of sight have been rewritten. Astronomers build models of this lensing effect to interpret the signals they detect. For without correction, the light from the star would mislead. What appears to be a single glowing patch may in fact be a warped image of 2 or more regions of the surface, folded together by gravity. This bending also affects the pulses we receive from rotating neutron stars. When beams sweep across the sky, the warping ensures that they are visible over a broader range of angles than they would be otherwise. The lighthouse becomes brighter and more persistent because gravity itself helps deliver the light to us. Without this bending, some pulsars would vanish from our sight, their beams missing Earth altogether. With it, the beams curve, their reach extended by the star's grip on space-time. To picture it, imagine standing on a cliff at night with a lantern. In the ordinary world, the light spreads out in straight lines. Anyone beyond the horizon will not see it. Now imagine the cliff itself warps space so that the light bends around it, circling back toward those who should be hidden. That is what neutron star gravity does to photons. It bends them back into visibility, expanding the star's presence in the sky. This phenomenon is a cousin of gravitational lensing on larger scales, where entire galaxies bend the light of more distant galaxies behind them, creating arcs and rings in the night sky. In the neutron star, the same principle applies, but on a compact and violent scale. The star becomes its own lens, reshaping the view of its surface. For astrophysicists, this complicates interpretation but also provides opportunity. The way the surface appears distorted carries information about the star's radius and mass. Since the degree of bending depends on compactness, the warping has another consequence. It blurs the line between what is above and what is behind. Light that seems to come from one part of the star may actually be photons bent from another. In this way, gravity not only holds matter in place, it twists vision, rewriting the very act of seeing. It reminds us that when we look at the cosmos, we are never looking at it unfiltered. We are looking through gravity's lens, which decides what we can and cannot see. And yet, through all this bending, the photons escape. Their paths may be twisted, their directions altered, but they are not trapped. Unlike in a black hole, where light curves inward endlessly, on a neutron star, the paths still open outward. Gravity has nearly won, but not fully. The photons reach us, bent and scarred, carrying an image of the star that is warped but not erased. In this bending, we see not defeat but resilience, the determination of light to find a way through, even when the road is crooked. As this part closes, we step toward the next question. If light is bent, how does this affect what we measure? How do astronomers translate distorted signals into clear understanding? The bending is not only a curiosity, it is a key to unlocking the star's shape and size. And in the following section, we will follow these distortions more closely, exploring how they become both obstacle and tool in the quest to understand neutron stars. The sight of a neutron star is not simple. What appears to us as a shining sphere is in truth a distorted projection, a surface bent by the very gravity that tries to hold light in place. When we look at it, we are not only seeing photons from the hemisphere facing us, we are also seeing photons that began on the far side, curving around the star before reaching our eyes. The result is a vision of more than half the sphere at once, a portrait that breaks the ordinary rules of geometry. This distortion changes how the star reveals itself. Hotspots on the surface, formed by magnetic funnels channeling matter, do not appear where they are. They are shifted, doubled, smeared across our detectors. A single pulse of light might be the combination of multiple warped paths, each bent by gravity before escaping. To measure a neutron star is to untangle these warped signals, peeling back the layers of distortion until the true surface can be glimpsed beneath. Astrophysicists model this bending with painstaking care. They trace paths of photons through curved spacetime, calculating how each trajectory curves depending on the compactness of the star. The compactness, the ratio of mass to radius, is the key. A more compact star bends light more severely. By comparing the observed distortions to the predicted ones, astronomers can constrain the size and weight of the star. In this way, the bending that seems at first to obscure actually becomes a tool, a lens through which the structure is revealed. This bending does more than change the view. It stretches time itself. A photon that curves around the star travels farther, arriving delayed compared to a photon launched straight outward. In pulsars, where beams sweep with clock-like regularity, these delays accumulate into patterns. By studying the timing of pulses, scientists can map the geometry of the bending, using time itself as a tracer of gravity. The experience of standing near such a star, if one could survive, would be disorienting. Look up, and the horizon would not appear as it does on Earth. Instead, the surface would seem to curve upward, wrapping around you, the far side visible above your head. The sky would be crowded with the star's own surface, bent into view. Space would feel smaller, curved inward, as though you were inside a mirrored dome. In that dome, light would be both guide and deceiver, showing you too much and yet never the whole. The warping is a reminder that vision itself depends on the rules of space-time. We take for granted that light travels straight, that what we see corresponds to where something island. But in the vicinity of a neutron star, that rule is rewritten. Straight lines no longer exist in the ordinary sense. Every path is curved, every sightline altered. What we call reality is filtered through a lens of gravity, and our understanding must adjust. Astronomers embrace this complexity because it is unavoidable. They simulate the light curves of neutron stars, calculating how hotspots rise and fall in brightness as the star rotates, accounting for bending and redshift together. The result is a map of how the star must be shaped. Without accounting for the bending, the data would make no sense. With it, the patterns fall into place, confirming the predictions of relativity in the most extreme environments. And yet, despite the distortions, light remains free. That is the essential contrast with a black hole. Near a black hole, photons that stray too close loop inward, circling endlessly or plunging across the horizon. No light escapes to tell the story. On a neutron star, photons may bend, curve, and delay, but in the end, they still find their way outward. The bending is severe, but it is not final. It shapes the message, but does not erase it. As this part comes to its close, we see the paradox clearly. Gravity twists the act of seeing, bends light until vision itself is distorted. Yet through that very distortion, we gain knowledge. What should confuse us instead reveals the star's compactness and mass. What should hide instead shows. Light, bent but not silenced, delivers the truth in warped form, and astronomers learn to read it. In the next section, we will explore this paradox further, following how these distortions expand into a deeper understanding of the neutron star's structure, and how they mark the last step before the ultimate trap of the black hole. The bending of light near a neutron star is more than a distortion of vision. It is a dialogue between gravity and photons, a dialogue written into every beam we receive. To see a neutron star is to witness that conversation. Each ray that reaches our eyes has traveled a path carved not by straight geometry, but by curved space-time. Each photon tells us, in its angle and delay, how steeply gravity pulls. This bending creates illusions. A hotspot rotating on the far side of the star may remain visible for longer than expected, because photons from its edge curve around and reach us. The pulses of a pulsar stretch and smear, but instead of hiding the star, these changes become signatures. Astronomers can use them to calculate the size of the neutron star with surprising accuracy. The amount of distortion becomes a ruler, a measure of compactness written into the light. But the distortions do more than extend our view. They show us the threshold where light itself begins to fail. As the star becomes more compact, the bending becomes stronger, until at last the escape velocity would equal the speed of light. In that case, photons launched outward would fall back, orbit endlessly, or plunge inward. That is the black hole's territory. A neutron star is the last stage before this crossing, where bending is extreme, but not total. In this way, it serves as a kind of cosmic warning, a marker of how close the universe can come to trapping light forever, without yet succeeding. To imagine what this bending means, consider what you would see if you hovered far above such a star. Instead of a clear disk showing one hemisphere, you would see a swollen globe revealing nearly 3/4 of its surface. The edges would blur into arcs of light, and the poles might appear distorted, shifted by the warping. What you would see is not the star as it is, but the star as gravity demands it be seen. In this way, the neutron star is both real and illusion, both surface and projection. The bending also blurs the line between the scientific and the poetic. It shows us that light is not free to move however it wishes, but must obey the shape of space-time. And yet, through those constraints, light still escapes, still delivers its message. It reminds us that truth can be warped but not erased, that knowledge can they complicate the task of interpreting observations, but they also enrich the data. Without bending, we would see less of the star and know less about it. With bending, we see more, and we are forced to reckon with relativity in its most dramatic form. The universe does not make knowledge simple, it makes it deep, layered, and sometimes disguised. Neutron stars are proof of this. Objects that hide and reveal at once. The importance of this bending extends beyond neutron stars themselves. It confirms that relativity is not only a theory for planets and stars, but for the most extreme realms of matter and energy. It shows that the same equations that describe the bending of starlight during an eclipse also describe the warping of light around a collapsed core. The continuity is striking. From the gentle curves of the sun's field to the violent twists of a neutron star, the same laws apply. And so we return to the central truth. The neutron star bends light, warps vision, and twists reality, but it does not silence photons. Unlike a black hole, it does not trap light within an event horizon. Its bending is severe, but still permissive. Photons can curve, delay, redshift, and smear, but they still emerge. This is the essence of the neutron star, the balance between crushing gravity and visible survival. As Chapter 4 ends, we look forward to the next revelation. Light is bent, warped, and redshifted, but it also carries rhythm. In some neutron stars, magnetic fields shape the light into beams that sweep across space with clock-like precision. These pulsars become beacons, their signals piercing through gravity and distance alike. They are the next stage in our journey, showing not only that light can escape, but that it can organize into patterns so regular that they become cosmic lighthouses, guiding our understanding across the galaxy. Among the many faces of neutron stars, one stands apart for its clarity and precision. These are pulsars, The cosmic lighthouses, neutron stars whose magnetic fields carve light into beams that sweep across space like the turning of a lantern on a dark sea. To encounter a pulsar is to encounter not just a collapsed star, but a rhythm, a heartbeat written into light itself, defying the crushing weight of gravity to proclaim its presence across the galaxy. The story of a pulsar begins with the rotation of the neutron star. When the massive core collapses in a supernova, angular momentum is conserved. A star that once rotated slowly, perhaps once every few days, shrinks to a radius of only 20 kilometers. The conservation of spin forces it to rotate hundreds of times each second. A skater pulling in her arm spins faster, and the same law applies here, but on a scale of stars. The result is staggering. Some pulsars turn so quickly that their surfaces move at a fraction of the speed of light, a city-sized sphere whirling with unimaginable speed. Wrapped around this spinning star is a magnetic field, trillions of times stronger than Earth's. The collapse compresses not only mass, but also magnetic lines of force. These fields are so intense that they channel charged particles into beams of radiation at the poles. As the neutron star rotates, those beams sweep across the sky. If Earth lies in their path, we see a pulse each time the beam points toward us. What we detect is not the star itself, but its rotating signature, a flash repeated with perfect regularity. The first pulsar was discovered in 1967 by Jocelyn Bell Burnell, who noticed a repeating signal in radio data, a series of pulses so regular that they seemed artificial. At first, the source was jokingly labeled LGM, for Little Green Men, because nothing in nature was thought capable of such precision. But soon other pulsars were found, and the truth became clear. These were neutron stars, collapsed remnants of supernovae, sending out beams like interstellar beacons. What seemed unnatural was in fact one of the most natural consequences of physics under extreme pressure. The pulses of a pulsar are astonishingly stable, some rival atomic clocks in precision, deviating by less than a second over millions of years. Ability makes them invaluable for science. Astronomers use them as cosmic timekeepers, measuring variations in pulse timing to detect planets, gravitational waves, and even to test relativity itself. Each flash of light or radio emission is a photon that has escaped the neutron star's gravity, bent and redshifted, but still carrying its message. The fact that these pulses survive at all, repeated endlessly, proves that light can endure even under the heaviest of burdens. To visualize a pulsar, picture a cosmic lighthouse turning in the dark. The beam is narrow, but its sweep covers vast distances. Across thousands of light years, through interstellar dust and plasma, the signal arrives. It is faint, but it is exact. Each pulse marks a rotation. Each rotation marks the persistence of the neutron star. The universe is noisy, filled with random explosions and turbulence, but the pulsar cuts through that chaos with steady rhythm. It is the ticking of a metronome set by collapse, the reminder that even in death, a star can keep time. The magnetic field that shapes these beams is itself a force of nature beyond comprehension. Trillions of times Earth's field, it is strong enough to rip atoms apart, to force electrons into bizarre spirals, to twist light into patterns no laboratory could produce. The beams it creates are not gentle rays but torrents of energy. Radio waves, X-rays, and gamma rays, bursting outward in streams that travel across galaxies. And yet, because of the star's rotation, we see them not as a steady glow but as pulses, sharp and precise, each one the flash of a cosmic lantern sweeping by. What astonishes scientists is not only that these beams exist, but that they remain visible for so long. A pulsar can keep its rhythm for millions of years, slowing only gradually as its energy leaks away into space. The slowing is so gentle that it can be measured pulse by pulse, allowing astronomers to trace the age and history of the star. In this way, pulsars become both clocks and fossils, records of collapse that endure long after the supernova fades. And so pulsars are more than curiosities. They are proofs. Each pulse is a photon that has escaped a gravity well nearly deep enough to trap light forever. Each pulse is bent, redshifted, delayed, but still precise, still true. They are evidence that even when gravity presses with unimaginable force, light can organize itself into rhythm, into pattern, into signal. To study a pulsar is to study the persistence of order against chaos, the survival of light against weight. As this first part closes, imagine standing on a planet orbiting such a star. The sky would flash with rhythm, each pulse a reminder of the collapsed giant at the center. It would be like living under a lighthouse that never falters, a clock that ticks not for years, but for cosmic ages. This is the power of pulsars, the most eloquent proof that light can not only escape, but can endure, carrying rhythm across the universe. In the next section, we will follow their signals more closely, seeing how their timing reveals secrets not only of neutron stars, but of space itself. The pulse of a neutron star is more than a flash of light. It is a statement of order, a rhythm imposed on chaos. In a universe where most signals are noisy, transient, or unstable, the pulsar's beat is steady. It is born from collapse, yet it persists with a precision that rivals the best clocks humanity has ever built. To listen to a pulsar is to hear the cosmos keeping time. Each pulse is created when the star's magnetic field funnels charged particles toward its poles. These particles accelerate to nearly the speed of light, releasing energy in beams that shoot outward along magnetic lines. As the neutron star spins, these beams sweep across the sky. If Earth lies in their path, we receive a pulse. The interval between pulses is simply the rotation period of the star. Some rotate once every few seconds, others hundreds of times each second. Each one is astonishingly stable, a rotation so regular that it can be measured down to fractions of a microsecond. This stability is not an accident. It is a direct consequence of the neutron star's enormous mass and compactness. The inertia of such a dense object resists disturbance. Once spinning, it continues to spin with nearly perfect constancy, slowed only by the gradual leakage of energy into space. Over time, the rotation slows, the pulses lengthen, but the change is so gentle that it can be tracked pulse by pulse across centuries. For astronomers, this provides a rare gift, a natural signal source that is steady, predictable, and incredibly precise. It is this precision that makes pulsars so valuable. By tracking the arrival times of their pulses, astronomers can detect minute changes in motion. If a planet orbits the pulsar, its tug shifts the star's motion, and the pulse timing changes in a way that reveals the planet's presence. In this way, the first exoplanets ever discovered were found, not around a sun-like star, but around a pulsar. The regular flashes of light carried evidence of worlds otherwise invisible. Pulsars also serve as probes of space-time itself. When two neutron stars orbit each other, their pulses reveal the gradual loss of energy through gravitational waves. By measuring the changing intervals of pulses, scientists confirmed that the stars were spiraling together, losing energy exactly as Einstein's equations predicted. This was one of the first indirect proofs that gravitational waves are real, decades before detectors like LIGO finally measured them directly. Thus, pulsars became laboratories of relativity, their precision allowing us to glimpse the ripples of space-time itself. The diversity of pulsars is another wonder. Some spin slowly, sending out pulses once every few seconds. Others, known as millisecond pulsars, spin hundreds of times each second, their beams flashing with frantic speed. These rapid rotators are thought to be spun up by accreting matter from companion stars, stealing angular momentum and accelerating their own rotation. They are the fastest clocks in the universe, whirling with such velocity that their surfaces nearly approach the speed of light. Yet even they remain stable, their pulses reliable across millions of years. Imagine the experience of detecting one of these signals. A telescope records radio waves arriving at regular intervals, like the beat of a drum. At first, it might seem artificial, too precise to be natural. But then the pattern is recognized, the source identified, and the realization dawns. This is the heartbeat of a dead star, a remnant of a supernova, spinning endlessly and broadcasting its rhythm across the galaxy. The sense of awe is immediate. Light, crushed and bent by gravity, emerges organized into pulses, carrying not only survival, but order. Pulsars also help us navigate. Their signals are so precise that they can be used as cosmic beacons, a galactic GPS. Spacecraft could one day orient themselves by listening to pulsars, just as sailors once guided their ships by the stars. The very objects born from collapse and destruction may guide future journeys through the void. In this sense, pulsars are both relics of death and tools for exploration, reminders that the universe can recycle catastrophe into guidance. And through all of this, the essential fact remains. Each pulse is a photon that has escaped. Each beam must climb the gravity well, redshifted, bent, and delayed, yet still reaching us. Gravity tried to silence it, but light survives, organized into rhythm. The pulsar is proof that not only can light escape, it can endure in patterns more stable than any machine we build. As this part closes, we carry forward the image of the pulsar as a cosmic metronome, a steady beat that echoes across time and distance. But the story does not end here, for while pulsars show us light organized into beams and pulses, they also show us what happens when magnetism itself rises to extremes. Beyond ordinary pulsars lie magnetars, neutron stars whose fields are trillions of times stronger than Earth's, where even light is bent and distorted by magnetism as well as gravity. To understand light's survival, there is to step into an even more hostile realm, where photons must struggle against both gravity and magnetic siege. That is the path ahead. The pulse of a neutron star carries more than rhythm. It carries memory. Each flash is the echo of a star that once burned with fusion, that collapsed under its own weight, that exploded in fire and left behind a remnant compressed into a sphere the size of a city. The fact that light still escapes, not randomly but in measured beats, is astonishing. It is as if the dead star has chosen to keep speaking, not with words but with the steady rhythm of its rotation. When astronomers detect a pulsar, they are not simply recording data, they are listening to time itself. The pulses arrive with such regularity that they can mark the passing of seconds, minutes, and years with accuracy better than most atomic clocks. Any tiny deviation from this rhythm becomes significant. A shift in arrival time by a fraction of a millisecond may signal a planet, a gravitational wave, or a starquake on the neutron star's crust. The pulsar is both a beacon and a seismograph, revealing its own tremors and the tremors of the universe around it. One of the most dramatic demonstrations of pulsar precision came from the Hulse-Taylor binary pulsar, two neutron stars locked in orbit around each other. By studying the pulses from one of the stars, astronomers observed that the orbit was shrinking, the stars slowly spiraling inward. The rate of decay matched exactly the predictions of Einstein's theory that gravitational waves were carrying energy away. This indirect evidence was so compelling that it earned a Nobel Prize, long before the direct detection of gravitational waves confirmed it. Light escaping a neutron star thus became the tool by which we glimpsed invisible ripples in spacetime. Even more extraordinary are millisecond pulsars. These spin hundreds of times each second, their beams flashing with near-instant regularity. To sustain such speed without tearing themselves apart seems impossible, but the immense gravity of the neutron star holds the structure together. These rapid rotators are believed to have been spun up by accreting matter from companion stars, stealing momentum until they whirl at the edge of possibility. The pulses they emit are so precise that they form the backbone of pulsar timing arrays. Networks of pulsars spread across the sky, used together as a galactic observatory for gravitational waves on scales larger than any single detector can probe. The stability of pulsars also hints at their eventual fate. As they lose energy, their rotations slow, their beams weaken, and at last, they fade into silence. But this process takes millions of years. In cosmic terms, it is a long and lingering afterlife. During that time, they guide us, teach us, and remind us that collapse is not always the end. The supernova destroyed the parent star, but the pulsar endures, a survivor broadcasting its rhythm to anyone who listens. It is tempting to think of these signals as mechanical, but they carry an emotional weight. To receive a pulse is to receive proof of survival. Light has not only escaped, but has organized itself into pattern, into order, into a clock that will not fail for ages. It is the triumph of rhythm over chaos, of signal over silence. When Jocelyn Bell Burnell first recorded those signals in 1967, she was hearing not aliens, but something stranger still. The heartbeat of a collapsed star, steady and precise across hundreds of light years. For humanity, pulsars are more than curiosities. They are guides, We have already engraved their positions and pulse rates onto plaques carried by spacecraft. Maps for any distant intelligence that might one day find them. In this way, pulsars become our markers in the galaxy. Our way of saying, here is where we are. Here is when we lived. The light that escapes them is not only survival but communication, a shared signal across species and across time. And so, as Chapter 5 draws to its close, we see that pulsars are not only beacons, but proofs. They prove that light can escape gravity's crushing hold, not in a scattered or weakened form, but in rhythm so steady it becomes a tool for science and navigation. They prove that even in collapse, the universe can produce order. They prove that death is not always silence, but sometimes a pulse that continues across the galaxy for millions of years. Yet even pulsars, with their beams and clocks, are not the most extreme form of neutron stars. There exists a rarer, more violent breed, magnetars, whose magnetic fields are so intense that they distort the very vacuum of space, twisting light itself as it escapes. If pulsars are lighthouses, magnetars are storms, violent and unpredictable, testing the limits of light's resilience even further. To continue our journey, we must now step into their domain, where light faces not only gravity, but also magnetic siege. If neutron stars are already extreme, magnetars are their most violent incarnation. These are neutron stars with magnetic fields so powerful that they defy ordinary description, where Earth's field protects us gently with a few Gauss, and where a hospital's MRI machine reaches tens of thousands of Gauss. The magnetic field of a magnetar can reach 1 quadrillion Gauss. That is 1 trillion times stronger than Earth's, so intense that it does not merely influence matter but twists the very vacuum of space itself. In this domain, light faces not only gravity's grip but magnetic siege, forced to thread its way through fields so strong they bend the rules of physics. The origin of magnetars lies in their birth. Some neutron stars are born spinning rapidly, their rotation amplifying their magnetic fields during collapse. The exact process is still debated, but the result is undeniable. A field of such ferocity that it stores energy enough to reshape the star's crust and unleash bursts more powerful than the sun emits in thousands of years. These bursts arrive on Earth as flashes of gamma rays, sudden and violent, capable of overwhelming detectors even from across the galaxy. Light that emerges from these storms is light that has survived not just gravity, but magnetic fire. The pressure of such a field is impossible to experience directly. On Earth, strong magnets can pull metal objects with visible force. In a magnetar's field, atoms themselves are elongated, stretched into filaments as electrons are forced into spiral paths along magnetic lines. Chemistry, as we know it, ceases to exist. Even the vacuum of space is altered, polarized in ways that split photons and twist their paths. This phenomenon, called vacuum birefringence, means that light passing through the field behaves as though the vacuum were a crystal, its polarization rotated, its path bent by invisible pressure. The consequences are immense. Magnetars are among the most violent sources of light in the universe. In 1979, detectors recorded a burst so intense that it briefly disrupted Earth's upper atmosphere, ionizing the air and altering radio transmissions. The source was a magnetar thousands of light years away. If such a burst occurred within a few dozen light years, it could devastate Earth's biosphere. Yet even from safe distances, we can feel their presence, their photons arriving as warnings of power barely constrained. And still, light escapes. Despite the crushing gravity of the neutron star and the shredding magnetism of the field, photons burst outward in floods. Some are polarized, some are bent, some are scattered, but they emerge. They carry signatures of the magnetic field, patterns in polarization that astronomers can measure. In this way, magnetars become laboratories not just of gravity, but of magnetism at its ultimate scale. Places where photons reveal how the universe behaves when magnetic fields rival or surpass all other forces. To imagine standing near a magnetar is to imagine impossibility. A human body would not survive a moment. The field would tear apart molecules, strip atoms, and reduce matter to subatomic fragments. Even at a distance of thousands of kilometers, the pull on electrons would be fatal. Spacecraft would fail, instruments would collapse, materials would shatter at the atomic level. The environment is not merely hostile, it is fundamentally incompatible with ordinary matter. Yet light, resilient and massless, threads the field. It is altered, it is twisted, but it is not destroyed. This resilience gives magnetars their paradoxical beauty. They are destroyers, capable of shattering crusts and blasting gamma rays across space. But they are also messengers, sending us photons that reveal their secrets. Each flash, each flare, is a message written in fire, telling us of fields too strong to imagine, of crusts cracking under pressure, of energy released in titanic storms. To observe a magnetar is to watch light survive under siege, to see photons escape even when every law seems to conspire against them. And as this part comes to its close, we carry forward the image of the magnetar as a cosmic storm, light struggling not only against gravity, but against magnetism so fierce it alters the vacuum itself. The question that follows is how these fields shape the star's behavior over time, how they unleash flares and quakes that shake the crust and flood the galaxy with light. In the next section, we will step deeper into the storms of magnetars, tracing how their flares remind us again that even in the most violent environments the universe can create, light still breaks free. The storms of magnetars are unlike anything else in the cosmos. Their surfaces are not stable crusts, but strange shells, locked against forces that twist and crack them. The magnetic field presses outward with such intensity that it distorts the shape of the star itself. At times, the pressure becomes too great, and the crust shifts violently in what astronomers call a starquake. When that happens, energy is released in bursts of X-rays and gamma rays, explosions that ripple across space with power beyond imagination. These flares can unleash more energy in a fraction of a second than the sun will emit in 100,000 years. The photons born in those storms must then fight their way out, not only against the pull of gravity, but against the tangled magnetic field that surrounds them. Some are scattered, some are polarized, some are delayed, but many escape. When they reach Earth, they trigger our detectors with sudden intensity, flashing warnings of violence from thousands of light years away. One of the most famous events occurred on December 27, 2004. A giant flare from the magnetar SGR 1806-20 lit up detectors around the world. For a brief instant, the energy output rivaled the brightness of the full moon, despite coming from 50,000 light-years away. The burst ionized Earth's upper atmosphere, disrupting radio communication. This was only a glancing blow, the echo of a cosmic quake. And still, it was felt across our planet. If such a flare happened much closer, it could strip atmospheres from worlds and alter the chemistry of life itself. In these moments, light is both destroyer and messenger. The gamma rays scorch and ionize, but they also tell us what has happened on the magnetar's surface. By studying the afterglow of these flares, astronomers learn how the crust cracks, how the field rearranges itself, and how matter behaves under pressures that no laboratory could replicate. The photons are marked by the journey. Their polarization carries the signature of vacuum birefringence. Their timing reveals the sequence of the quake. Their energy shows the scale of the release. The resilience of photons in such storms is almost paradoxical. Magnetars generate environments that crush molecules, bend vacuum, and fracture crusts. Yet light still finds its way outward. The reason lies in the nature of the photon itself. Massless, it is not trapped by magnetic fields in the same way charged particles are. It can be bent, twisted, delayed, but it cannot be held forever. In this way, light becomes the only witness that escapes the siege, the only carrier of the story to the wider galaxy. Theoretical models suggest that magnetars may also generate fireballs of plasma trapped in their magnetic loops. Within these loops, photons may bounce back and forth before finally escaping in a cascade. What reaches us then is not a simple flash, but the aftermath of countless interactions. Photons, shaped by the tangled geometry of both space-time and magnetic field. Each detection is the end of a labyrinthine journey, a photon that has slipped past obstacles unimaginable to us. To observe a magnetar is to see the limits of survival for light. Gravity nearly traps it. Magnetism nearly twists it out of existence. Yet photons still break free. The cost is written in their altered properties, but their persistence is undeniable. For astronomers, this is more than an observational triumph. It is a reminder that even the most crushing environments cannot silence light completely. And so, as this second part closes, we are left with an image of the magnetar as both destroyer and storyteller. It fractures its own crust, unleashes flares across the galaxy, and yet allows photons to escape, carrying the record of its violence. The next step is to look more closely at how these flares affect not only distant detectors, but even Earth itself. How light traveling across thousands of light years can still have power enough to touch our planet and alter its atmosphere. That is where the story leads us next, into the final act of this chapter. The reach of magnetars is not confined to their immediate surroundings. Their light can travel across thousands of light years, and even at that distance, it can leave an imprint on Earth. The flare of 1979 from SGR 0526-66 ionized our ionosphere, disrupting radio waves as though a solar storm had struck. The flare of 2004 from SGR 1806-20 shook instruments worldwide. These were not nearby stars. These were events unfolding halfway across the galaxy, and still their light carried enough power to disturb our atmosphere. That is the measure of their violence. The thought is unsettling. A single starquake, in a star we cannot see with the naked eye, can reach across space and touch our world. Yet, it is also a reminder of light's resilience. The photons that caused those disturbances had traveled for tens of thousands of years. They had been bent, polarized, and redshifted, but they had not been extinguished. They endured long enough to arrive and announce their origin. They told us that a magnetar had cracked, that a storm of energy had burst forth, and that light, once again, gravity and magnetism are not the only forces that shape light near a neutron star. The thin veil of atmosphere that clings to its surface plays its part as well. Though no thicker than a fragile skin, this atmosphere scatters, absorbs, and filters the photons that rise. It adds its own mark to the light that escapes, complicating the picture further. To continue, we must look at this delicate layer, where radiation and matter struggle in balance, and where light's journey begins not from the bare crust, but through a shifting ocean of particles. The surface of a neutron star seems like it should be bare, an exposed crust of degenerate matter, pressed into solidity by gravity so intense it defies comparison. Yet above this surface, there exists a veil, a whisper-thin atmosphere clinging against overwhelming odds. It is no thicker than a few centimeters, but it is enough to change the way photons escape. This fragile layer is the star's skin, the medium through which radiation must pass before it can break free into space. In that passage, light is filtered, scattered, and shaped, carrying the imprint of the atmosphere along with the mark of gravity itself. The material of this atmosphere depends on the history of the star. Some neutron stars retain a coating of hydrogen, the lightest and simplest element, gathered from space or left behind after the supernova. Others hold helium, or even heavier elements dredged up from deeper layers. Whatever the composition, the pressure is beyond ordinary comprehension. A centimeter beneath the surface, the density can exceed that of lead. Atoms are stripped of their electrons, leaving only ions and free particles swirling in a plasma heated to millions of degrees. In such a furnace, chemistry as we know it does not exist. Photons born in the star's crust must climb through this atmosphere before they can escape. Along the way, they scatter off electrons, are absorbed and re-emitted by ions, and are filtered according to the properties of the plasma. This process alters not only their energy, but also their direction, softening sharp bursts into broader emissions. The light that finally escapes is no simple reflection of the crust below, but a message modified by its passage through a storm of particles. Radiation pressure also plays its role. Near the surface of a neutron star, the flux of photons is so great that it can push back against gravity itself. This balance sets a limit called the Eddington luminosity, the maximum brightness a star can sustain before radiation lifts the atmosphere outward. For most neutron stars, gravity wins easily, pinning the atmosphere in place. But during bursts, when nuclear reactions on the surface ignite, the flood of photons can approach this limit. The atmosphere swells, expands, and then collapses again as the outburst subsides. To us, watching from afar, These events appear as X-ray bursts, sudden spikes of radiation that brighten and fade with dramatic speed. Such bursts reveal the struggle of light against gravity at its most vivid. They occur when hydrogen or helium accreted from a companion star ignites in runaway fusion, releasing enormous energy in a brief flash. Photons surge outward, straining against the atmosphere, lifting it momentarily before gravity slams it back down. Each burst is a heartbeat of the neutron star, a flare of energy that escapes the crushing weight for only a moment. The photons that reach us from these bursts tell us not only about fusion, but about the density, thickness, and behavior of the atmosphere itself. Astronomers have learned to read these bursts as diagnostic tools. The rise and fall of brightness, the timing of the peak, and the spectrum of escaping photons all reveal the conditions on the surface. From them, scientists infer the mass and radius of the neutron star, the composition of the atmosphere, and the balance between gravity and radiation pressure. Each burst becomes a probe, each photon a clue to the star's hidden structure. And yet, despite its power, the atmosphere remains astonishingly thin. Compared to the Earth's air, which stretches for hundreds of kilometers, the atmosphere of a neutron star is nearly non-existent. It clings by the force of gravity alone, and even the strongest outbursts cannot expel it completely. It is a reminder that in these extreme places, scale is deceptive. What would be vast on Earth is fragile here, and what is fragile here would crush anything from Earth in an instant. The photons that rise through this atmosphere are survivors of two battles at once. First, they climb against the 200 billion times gravity of the neutron star. Then, they thread their way through a plasma of particles that scatter and absorb them. By the time they emerge, they are marked by both struggles, their energies redshifted by gravity and filtered by the atmosphere. When we study them, we are not seeing pure light from the crust, but a layered message, each layer shaped by a different force. As this first part closes, the atmosphere emerges not as an afterthought, but as a stage in light's escape. Without it, the photons would tell a simpler story. With it, they carry a richer one, marked by scattering, bursts, and balance between radiation and gravity. In the next section, we will step deeper into these bursts, following the way they flare and fade, and seeing how, even in the fiercest moments of nuclear ignition, light still escapes to carry the secrets of the neutron star across the cosmos. The atmosphere of a neutron star is both veil and crucible. Though only centimeters thick, it holds the power to shape every photon that emerges. The heat from below drives the plasma into a restless dance, while gravity presses downward with billions of times the strength we know on Earth. In this clash, bursts of radiation become tests of balance, moments when photons rise in numbers so great that they nearly unseat gravity itself. These events are most vividly seen in X-ray bursts, brief flares that brighten a neutron star for seconds or minutes. They occur in systems where matter from a companion star rains down upon the neutron star, forming an accretion disk that feeds the surface. Hydrogen and helium pile up in the thin atmosphere, compressed by gravity, until conditions for nuclear fusion are met. Then, in an instant, the fuel ignites. The reaction spreads like wildfire, burning across the surface in a runaway release of energy. Photons pour outward in torrents, hammering against the atmosphere, swelling it outward against gravity. From Earth, these bursts appear as sudden spikes in brightness, recorded by X-ray telescopes. The rise is sharp, the fall gradual, a curve that astronomers study with precision. The timing of the burst, the peak intensity, and the cooling tail all reveal details of the star's surface and atmosphere. Each burst is a natural experiment in high-energy physics, a chance to see how matter behaves when compressed beyond terrestrial limits. The photons that arrive are not random. They carry the mark of fusion, the stamp of gravity, and the filter of the atmosphere. Sometimes, the radiation pressure in these bursts becomes strong enough to lift the atmosphere outward temporarily. The photosphere expands, doubling or tripling in radius before collapsing back down as the burst fades. This is known as photospheric radius expansion, and it is one of the most direct demonstrations of how radiation pressure can oppose gravity even on a neutron star. The light itself pushes back against the crushing weight, expanding the thin atmosphere before surrendering to the inevitable return. Photons in these moments are warriors, fighting a battle they cannot win, but still leaving their mark in the struggle. These bursts also provide a way to measure the distance to neutron stars. When the atmosphere expands to the point where radiation pressure balances gravity, the luminosity reaches the Eddington limit, a universal threshold. By comparing the observed brightness to this intrinsic luminosity, astronomers can calculate how far away the neutron star must be. Thus, the bursts not only reveal the physics of the atmosphere, but also map the star's place in the galaxy. The composition of the atmosphere shapes the bursts as well. A hydrogen-rich layer burns differently than helium, producing distinct signatures in the photons that escape. By studying these differences, astronomers can infer what elements coat the surface, how accretion proceeds, and even how the nuclear reactions unfold. In this way, the thin atmosphere becomes a stage for nuclear physics as much as astrophysics, a place where elements ignite and light records the fire. To imagine such a burst is to imagine fire constrained by gravity beyond imagining. A wave of fusion ignites across the surface, releasing energy greater than billions of hydrogen bombs in a matter of seconds. Photons surge upward, colliding with electrons, scattering through the plasma, straining against gravity, and finally breaking free into space. They travel across thousands of light years, and when they arrive, they appear on our detectors as a flicker, a brief flare, a line on a chart. Yet behind that flicker lies violence greater than anything Earth has ever known. Even between bursts, the atmosphere plays its quiet role. Photons from the hot surface scatter and diffuse through the plasma, softening into a thermal spectrum. The light we see is not the raw heat of the crust, but the filtered glow of an atmosphere only centimeters thick. In that thin skin lies the final shaping of the message, the last modulation before photons are released to the universe. Without it, the neutron star would shine differently, and we would lose one of the richest sources of clues about its true structure. As this part comes to its close, the atmosphere emerges as both obstacle and messenger. It resists photons, scattering and filtering them, yet it also encodes information that allows us to understand the star's surface, its bursts, its distance, and its composition. The photons that reach us have survived not only gravity but this final layer, altered but enriched, carrying knowledge across space. In the next section, we will follow these photons further, exploring how repeated bursts and quiet emissions confirm theory again and again, proving that light, though challenged, always escapes. The quiet persistence of a neutron star's atmosphere may seem trivial beside the crushing gravity and violent magnetism we have seen before, but its role in shaping light is profound. Without it, photons would pour directly from the crust into space. With it, they are sifted, scattered, and softened, their message altered in ways we can measure. This final veil is delicate, but it leaves a lasting fingerprint on every photon that escapes. Repeated bursts confirm this truth again and again. Each flare of nuclear fusion on the surface produces a surge of photons, and each surge interacts with the atmosphere in ways that reveal its properties. The timing of the burst tells us how fuel accumulates. The energy of the photons shows us how the plasma behaves. The fading tail of the burst maps how heat diffuses through the thin layer. Each observation is an experiment the star conducts for us, and each photon is a data point carried across light years. Even in the absence of bursts, the atmosphere plays its part. The steady glow of thermal radiation from the surface must pass through the plasma, emerging as a spectrum we can study. By analyzing that spectrum, astronomers can test theories of dense matter, measuring the size and mass of neutron stars indirectly. The photons tell us about the crust, but they also tell us about the skin, about the layer that shapes their final form before release. This atmosphere also illustrates a deeper principle. Even in a place where gravity presses with 200 billion times Earth's pull, where matter collapses into neutrons and protons, there is still room for delicacy. A layer no thicker than a book can shape the light of an entire star. Fragility and force coexist, side by side, in ways that challenge our sense of scale. The universe, it seems, allows no feature to be dismissed as too small to matter. When telescopes like NICA aboard the International Space Station peer at neutron stars, they measure these effects with exquisite detail. The arrival times of X-rays, the shape of their energy distribution, and the subtle shifts caused by redshift and atmosphere combine to paint a portrait of the star. From these portraits, scientists deduce not only the size and weight of neutron stars, but also the nature of matter at nuclear densities. Light, shaped by atmosphere, becomes a translator of physics we cannot touch. And so, the atmosphere joins gravity and magnetism as another gauntlet that photons must run. Gravity tries to hold them, magnetism twists them, and atmosphere filters them. Yet photons emerge, carrying the record of every trial. They reach us changed but enriched, not weakened but marked. Each alteration is not a loss, but an addition, a layer of meaning written into the message of light. As Chapter 7 closes, we are reminded again that nothing about neutron stars is simple. Their atmospheres may be thin, but they are decisive. Their bursts may be brief, but they are illuminating. Their photons may be altered, but they are truthful. And as always, the fact that light escapes at all is a triumph. Ahead lies the starkest contrast of all. We have seen how light survives in neutron stars, altered but unbroken. But what happens when gravity grows so strong that escape velocity equals or exceeds the speed of light? That is the realm of the black hole, where no photon emerges, where light's story ends at the event horizon. To grasp the difference is to understand why neutron stars are the last outpost before the ultimate silence, the place where light still resists, just before it is lost forever. A neutron star is gravity on the brink. It bends light, slows time, and presses matter into densities beyond imagination. But it does not fully conquer photons. They still climb out, redshifted, bent, and altered, yet still free. But if the balance tips just a little further, if the mass grows just enough, gravity crosses a threshold. That threshold is the event horizon of a black hole, a boundary not of matter but of geometry, beyond which no light can ever return. The difference between a neutron star and a black hole lies in escape velocity. At the surface of a neutron star, the escape velocity is nearly half the speed of light. Photons move faster than that, and so they can still break free. But in a black hole, the escape velocity equals or exceeds the speed of light. No matter how fast a particle tries to climb, it cannot outrun the inward slope of spacetime. Even light, with no mass and the fastest speed allowed by the universe, is held captive. The event horizon is therefore not a physical surface but a point of no return, the place where escape becomes impossible in principle. This distinction makes neutron stars the last outposts where light survives. They are thresholds, edges of visibility in a cosmos where collapse can continue further still. A neutron star says, "I am dense enough to challenge light but not to silence it." A black hole says, "Here, light ends." To understand this difference is to understand the boundary between what can be observed and what is hidden forever. Imagine standing at the surface of a neutron star. Gravity presses down, time slows, and light struggles upward but eventually emerges. Now imagine the same for a black hole. There is no surface, no crust to stand upon. Instead, there is an invisible horizon. Cross it, and all paths lead inward. The photon emitted just below cannot climb out. The photon emitted just above still can, but only if aimed outward with perfect precision. This razor-thin boundary defines the black hole, an edge as absolute as it is invisible. And yet, from the outside, the two objects can seem deceptively alike. Both are compact, both bend light, both redshift photons, both warp space so strongly that vision itself is distorted. The difference lies in the outcome. In a neutron star, distortion is severe but not final. In a black hole, distortion becomes silence. The star collapses past the point where neutrons can resist, and no pressure remains to hold it up. Space-time curves inward without limit, and the result is a shadow in the fabric of the universe. Astronomers have begun to see these shadows directly. With the Event Horizon Telescope, they have imaged the silhouette of a black hole against glowing plasma. What is seen is not the black hole itself, but the absence of light, the shadow where photons are swallowed. In contrast, when we observe neutron stars, we see light, even if it is bent, redshifted, and altered. That light is the difference between visibility and oblivion, between resistance and surrender. The symbolism is profound. Neutron stars are survivors. They resist collapse. They allow photons to escape. They tell their story in pulses, bursts, and beams. Black holes are finalities. They offer no photons, no signals, only silence where light is lost. Between the two lies the razor edge of nature, the thin balance of pressure and mass that decides whether light endures or vanishes. As this first part draws to a close, we carry forward the image of neutron stars as the last frontier before silence. They are not black holes, though they teeter at the brink. They are reminders that light can survive incredible odds, but only up to a limit. Beyond that limit lies the horizon, the place where light ends its journey. In the next section, we will follow this contrast more deeply, exploring how neutron stars differ from black holes in both theory and observation, and how the photons that escape from one highlight the silence of the other. The distinction between neutron stars and black holes is a lesson written in extremes. Both are born from the collapse of massive stars. Both emerge from the violence of a supernova, when the core implodes and outer layers are cast into space. But where the neutron star halts, balanced precariously by the pressure of neutrons, the black hole continues. It crosses the boundary, where even that last pressure fails, leaving only gravity unchecked. For the neutron star, escape velocity remains less than the speed of light. Photons can still flee, though they lose energy in the climb. We see them as X-rays, as pulses of radio waves, as flares of gamma rays. They are altered but present. For the black hole, escape velocity equals or exceeds the speed of light. No photon can escape, no signal can emerge. The result is an object that is invisible, except through the effects it has on its surroundings. Where neutron stars speak in pulses, black holes speak in silence. And yet, the silence itself can be studied. Around a black hole, matter falling inward heats to extreme temperatures, releasing torrents of X-rays before crossing the horizon. Jets of plasma erupt from the poles, driven by magnetic fields tapping into the black hole's spin. These emissions are not from within the horizon, but from the region around it, the accretion disk and the corona, where light can still break free. By contrast, neutron stars have surfaces. Matter falling onto them strikes solid crust, releasing light in bursts that carry direct information about the star. The difference between a surface and a horizon is the difference between visibility and erasure. General relativity predicts that near a black hole, time itself is distorted to the point of stasis. To a distant observer, a photon emitted just above the horizon takes infinite time to climb away. The light fades, redshifted beyond detection, until it vanishes. In a neutron star, the redshift is immense but finite. We can still measure it, still record the photons. The star does not silence them completely. That is why neutron stars remain precious. They show us the brink of collapse without crossing it, giving us access to physics at the threshold of invisibility. This contrast becomes clear when astronomers attempt to measure mass and radius. For neutron stars, the redshift and bending of light carry clues to their structure. Observations of bursts, pulses, and emissions allow us to calculate their compactness. For black holes, no such direct light exists. We measure their mass and spin only by how they influence nearby matter. Their interiors remain hidden, their horizons absolute. Light is the messenger of knowledge, and where light is silenced, mystery deepens. It is tempting to see the neutron star as a fragile survivor and the black hole as its inevitable successor. Yet the cosmos shows us both existing in balance. Some stars collapse into neutron stars, others into black holes, depending on their mass. Some neutron stars may eventually accrete enough matter to cross the line and become black holes, surrendering their light forever. The universe does not choose one or the other. It allows both, side by side, as examples of what gravity can achieve when it pushes matter past its limits. To imagine the difference, picture two remnants of death. One shines faintly, its light altered, its photons struggling but escaping. The other is dark, its photons trapped, its presence known only by the shadows it casts on nearby matter. Both are children of collapse, but one resists silence while the other embraces it. The neutron star whispers, the black hole swallows. The distinction is absolute, yet the two are connected, two outcomes of the same process, two stages of the same story. As this part closes, we prepare to explore the edge more closely. How does light behave at the threshold of the event horizon? How do the differences between surfaces and horizons shape our understanding of what we can and cannot know? In the next section, we will follow the comparison to its conclusion, tracing how neutron stars reveal what black holes hide, and how light, escaping one but not the other, defines the boundary between knowledge and mystery. The neutron star and the black hole are siblings born of collapse, yet their destinies diverge in the most decisive way. One allows light to escape, though changed, while the other silences it forever. This contrast makes them mirrors of each other, teaching us not only about gravity, but about the limits of what we can know. When we study neutron stars, we do so through photons. Every pulse, every burst, every redshifted spectrum is a message that crossed space to reach us. We can measure their masses, their radii, even hints of their internal structure, because light escapes to tell the story. When we study black holes, light is absent. We learn only by watching how matter behaves around them, how disks of plasma swirl and heat, how stars in orbit accelerate under unseen weight. The silence of the black hole is as telling as the whispers of the neutron star. The event horizon is not a surface of matter, but a surface of no return. Cross it, and there is no signal, no photon, no particle that can escape. The difference between just outside and just inside is absolute. For the neutron star, there is still resistance. Neutrons pressed together create a pressure that halts collapse, and photons can climb free. For the black hole, nothing halts the inward rush, and the fabric of space curves so steeply that all paths turn inward. This makes neutron stars the last boundary of visibility, the final place where light endures before gravity claims victory. The practical implications are immense. Observations of neutron stars allow us to probe physics at nuclear densities, to test general relativity, and to measure the properties of matter under extremes. Observations of black holes show us the behavior of matter in their neighborhoods, but reveal nothing of their interiors. Light makes the difference. Where it escapes, knowledge flows. Where it is silenced, mystery reigns. And yet, even the silence of black holes has meaning. Their shadows, imaged by the Event Horizon Telescope, are framed not by light they emit, but by light they devour. The contrast between the glowing plasma and the dark void outlines the horizon itself. It is an indirect vision, but still a vision, one that confirms that the horizon is real. In this way, black holes remain connected to neutron stars, both defined by the fate of light in their presence. The symbolism is striking. The neutron star is a whisper of resistance, a reminder that even crushed matter can still let photons go. The black hole is surrender, the point where resistance ends and silence begins. Together they form a cosmic continuum, from endurance to silence, from altered light to absent light. To contemplate them is to see how finely the universe balances on the edge between what can be known and what must remain hidden. As Chapter 8 ends, we carry forward the lesson that light defines the boundary. Neutron stars show us the brink, where photons emerge, redshifted, bent, but still alive. Black holes show us what lies beyond, where light vanishes and knowledge halts. Between the two is the edge of visibility, the razor line where gravity nearly wins. The next step is to return to the light itself, not in theory, but in practice. How do we, on Earth, detect the photons that survive these journeys? What instruments capture them? What telescopes measure their redshift? What arrays decode their pulses? In the next chapter, we follow the tools of observation, the machines that allow humanity to read the messages photons carry from the edge of collapse. Light that escapes a neutron star is a messenger. It has climbed out of gravity's pit, endured scattering in the atmosphere, bent its path through curved space-time, and crossed light years to arrive at our small corner of the galaxy. But its journey is not finished until it is caught, measured, and translated by human instruments. To us, the photon is invisible until it collides with a detector. The story it carries remains silent until we learn to read it. The challenge is immense. The photons that reach us are faint, scattered by interstellar gas, their energies altered by redshift and bending. They arrive in bands of the spectrum that our eyes cannot see, X-rays, gamma rays, and faint radio pulses. To detect them requires machines built not only with precision but with imagination. Machines that can translate what no human sense can perceive into signals we can understand. The telescopes that serve this role are not just instruments, they are extensions of our senses, stretching our reach to the most violent corners of the cosmos. Consider the Chandra X-ray Observatory. Launched into space in 1999, it was designed to catch the high-energy photons from neutron stars, photons that Earth's atmosphere would otherwise block. Its mirrors are not ordinary glass, but carefully shaped surfaces that deflect X-rays at shallow angles, guiding them into detectors with delicate precision. Each photon that enters is recorded, its position, time of arrival, and energy measured. From these data, astronomers reconstruct images of pulsars, magnetars, and bursting neutron stars, turning invisible radiation into maps of the extreme. NICER, the Neutron Star Interior Composition Explorer, is another sentinel. Mounted on the International Space Station, it peers at neutron stars with exquisite timing accuracy. Its detectors record the arrival times of X-rays down to microseconds, allowing scientists to measure the pulsations of neutron stars with unmatched detail. From this timing, they infer the star's size, its rotation, and the bending of light around it. NICER does not simply watch, it listens to the heartbeat of neutron stars. Each pulse, a photon, escaping gravity's grip. Then there is XMM Neutron, launched by the European Space Agency. It collects more photons than Chandra, giving it the sensitivity to measure faint spectra from distant neutron stars. By analyzing the subtle redshift of absorption lines in these spectra, astronomers confirm the predictions of relativity, measuring how much energy photons lose as they climb away. Each shift is small, but together they form proof that gravity leaves its mark on light. On Earth, radio telescopes, such as the giant dish at Arecibo before its collapse, or the networks of dishes in arrays like the Very Large Array, listen for pulsars. They do not collect light in the visible sense, but they catch radio waves, photons stretched to long wavelengths by magnetic processes near neutron stars. Each pulse they record is a photon's survival story, a beam that has crossed space to arrive in rhythm. By combining many telescopes across continents, in a technique called very long baseline interferometry, astronomers sharpen their vision, resolving details finer than any single dish could see. These instruments are humanity's eyes and ears on the extreme. Without them, neutron stars would remain abstract, numbers in equations and predictions on paper. With them, they become voices, each photon a word, in a language we are learning to speak. The detectors are translators, turning invisible radiation into charts, images, and signals. They allow us to not only know that light escapes, but to measure how, in what form, and with what message. As this first part comes to its end, we see that the triumph of light is incomplete without the triumph of detection. Photons that escape neutron stars travel immense distances, but their survival is meaningless unless they are caught. The machines we have built, from orbiting X-ray observatories to radio arrays on Earth, are the final stage of the journey. They are the places where the story of the photon is received, decoded, and shared. In the next section, we will follow how these observations translate into knowledge, how gravitational redshift, bending, and bursts are measured directly, and how light becomes data that tells us the structure of the most extreme stars in the cosmos. The photons that leave a neutron star do not arrive as a simple stream of light. They arrive encoded with information, each one carrying a fragment of the star's story. To read that story, astronomers must measure not only brightness but also spectrum, timing, and polarization. Each property is a clue. Together, they form the grammar of light, the way photons tell us what they endured on their way from the surface of the star to our instruments. The spectrum of light is often the first layer of information. When photons are separated by energy, they reveal which processes produce them. X-ray bursts from nuclear burning have a thermal spectrum, peaking at energies consistent with plasma, millions of degrees hot. Pulsar beams produce non-thermal spectra, shaped by magnetic acceleration. Absorption lines, faint dips in the spectrum, reveal the presence of elements in the atmosphere. When these lines are redshifted, astronomers measure directly how much energy photons have lost to gravity. A tiny shift in wavelength becomes evidence of a force 200 billion times stronger than Earth's gravity. Timing is the second layer. Photons from pulsars arrive in pulses, their intervals marking the rotation of the star. Instruments like NICA record the arrival times of photons down to millionths of a second, building a map of the star's spin. Variations in timing reveal companions tugging on the neutron star, glitches in rotation when the crust cracks, or the slowing of the spin as energy leaks away. Each shift is recorded not in words but in the steady rhythm of photons, a ticking that outlasts civilizations. Polarization is a newer but powerful layer. In strong magnetic fields, light can become polarized, its electric field aligned in a preferred direction. Detecting polarization in X-rays from neutron stars tells us how photons were twisted by the magnetic field or by vacuum birefringence near the star. Polarimeters, instruments designed to measure this property, are just beginning to reveal new dimensions of the story. The alignment of photons becomes another testimony, another imprint of survival under extreme conditions. Even the absence of photons is a form of information. A gap in pulses may signal that the beam has shifted or that the magnetosphere has reconfigured. A sudden silence in a once steady pulsar can mean a starquake or a rearrangement of magnetic fields. Light does not only speak through presence, but also through absence, and astronomers learn to read both. The data collected are immense. A telescope in orbit records millions of photons from a single source, each marked with time, energy, and direction. Supercomputers sift through the data, separating signal from noise, building light curves, spectra, and timing models. What begins as a chaotic rain of photons becomes a coherent picture. The mass of a neutron star, the radius of its surface, the strength of its magnetic field. The photons do not just tell us that they escaped, they tell us what they escaped from. To imagine the process is to imagine listening to a choir across a great distance. Each voice is faint, distorted by wind and distance, sometimes silenced altogether, yet with enough patience and the right instruments, the melody emerges. The photons are those voices, and the neutron star is the choir, singing across light years through distortion, scattering, and bending. We catch fragments, but from them we reconstruct the song. As this part draws to its close, we see how essential observation, island light, may escape. But without instruments to measure it, the story would remain untold. With spectrum, timing, and polarization, we decode photons into knowledge. We turn survival into science. In the next section, we will follow how these tools of observation transform not only photons into data, but data into theory. How light tells us of densities, pressures, and structures that define the very edge of matter. Detection is only the beginning. Once photons are recorded, their meaning must be extracted. Numbers on a detector are not knowledge until they are interpreted. And interpretation requires both theory and imagination. Each spectrum, each pulse train, each burst curve is compared against models of how light should behave when escaping neutron stars. When the data match the prediction, the theory is confirmed. When they diverge, new questions arise, forcing deeper investigation into the physics of matter under pressure. From this cycle of observation and theory, entire fields have grown. The measurement of gravitational redshift in neutron star spectra has confirmed Einstein's prediction that light loses energy as it climbs away from massive bodies. The detection of pulse delays and bending has validated models of curved spacetime. The analysis of X-ray bursts has revealed the details of nuclear fusion in extreme environments. All of these insights are possible only because photons endured their journey, and because we caught them with machines tuned to hear their faint voices. Sometimes the light itself guides us to new frontiers. Pulsar timing arrays use the steadiness of pulses to search for gravitational waves from orbiting black holes in distant galaxies. The rhythm of light becomes a probe of spacetime ripples larger than any laboratory can measure. Magnetar flares, caught by satellites, tell us about vacuum birefringence and the limits of magnetic fields. Each detection expands the boundaries of what we can test, turning neutron stars into natural laboratories. The collaboration between instruments is also essential. A burst seen in gamma rays may be followed by X-rays, then by radio afterglows. Space telescopes orbit above the atmosphere to catch high-energy photons, while ground-based dishes listen for the long, low tones of radio. Together, they weave a full picture from fragments, each instrument capturing one part of the spectrum, one part of the story. Without this coordination, much would be lost. With it, the puzzle of the neutron star becomes clearer piece by piece. And yet, even with all our tools, the challenge remains enormous. Neutron stars are distant, their signals faint, their photons rare. Many bursts go unnoticed, many pulses too weak to be detected. What we see is only a fraction of what occurs, but that fraction is enough. It is enough to confirm relativity, to test nuclear physics, to map the limits of matter. It is enough to remind us that light, however challenged, still arrives. The process transforms light into knowledge. A photon begins as a vibration of fields on a collapsing star, escapes gravity, crosses space, and ends as a pulse in a detector. From there, it becomes a data point, a line on a graph, an entry in a model. With thousands or millions of such points, patterns emerge. The patterns become laws, and the laws become understanding. In this way, light is not only survival but revelation. It is the path from silence to knowledge, from collapse to meaning. As Chapter 9 closes, we stand at the end of the photon's journey. From its birth in the depths of a neutron star to its detection in our machines, it has survived battles with gravity, magnetism, atmosphere, and distance. And when we catch it, we learn. We learn not just about stars, but about the universe itself, about the rules that govern matter and light at their most extreme. But the journey of the book is not finished. We have seen how gravity almost silences light, how photons endure distortion and bending, how bursts and pulses carry messages across space, and how our instruments decode them. Now, in the final chapter, we must gather these threads together. We must look at the triumph of light as a whole, at its resilience, its symbolism, its ability to survive the most crushing environments the cosmos has to offer. For even at the brink of silence, light endures, carrying the story of death and survival across the stars. Across every chapter of this journey, light has been challenged, bent, slowed, and filtered. Yet it has always endured. From the birth of a neutron star in the fire of a supernova, photons have faced obstacles that should have silenced them. Gravity pressed with 200 billion times the strength of Earth. Magnetic fields tore at the vacuum itself. Atmospheres scattered and absorbed, yet still light emerged. That survival is more than a physical fact. It is a triumph, a reminder that even in the harshest places the cosmos can create, photons refuse to vanish. To see the story whole is to see the balance between weight and endurance. When the core of a massive star collapses, matter is crushed into densities beyond comprehension. Neutrons press against each other, resisting further collapse, halting just before the point of no return. Light born in that crucible must then climb outward, carrying the memory of the collapse. It loses energy, its frequency stretched into redder bands, but it escapes. Each photon that reaches us is a survivor of that collapse, an echo of a star's death traveling across the galaxy. We have followed light as it bent around the curved geometry of space-time, wrapping photons from the hidden side of the star into our view. We have traced it through pulsars, where magnetic funnels turned it into beams so precise that they rival clocks in stability. We have seen it endure the storms of magnetars, where even vacuum is polarized, and still find a way through. We have watched it thread the thin atmosphere, scattering, shifting, and yet carrying signatures we can measure. At every step, gravity nearly won, but not fully. This resilience is not only physical but symbolic. Light is knowledge. Where photons survive, information survives. Where they are silenced, mystery deepens. Neutron stars stand at the edge of silence, at the brink of black holes, where light ends forever. Their photons remind us that even on the edge, there is still resistance, still survival, still meaning to be carried outward. They are the last voices before silence, the final messengers before the event horizon. The triumph of light is also our triumph. Without it, we would know nothing of these stars. We cannot touch them. We cannot send probes to their surfaces. We cannot survive their gravity. All that we know comes from photons, from their endurance across impossible conditions. Every equation tested, every mass measured, every radius calculated is built upon their persistence. To study neutron stars is to rely on light's ability to escape and to carry truth across light years. As this first part of the final chapter draws to its close, we stand with the knowledge that light is not merely a feature of neutron stars, but their victory. It is the thread that connects collapse to survival, silence to knowledge, destruction to meaning. In the next section, we will gather more of these threads, reflecting on how the resilience of photons carries lessons not only for physics, but for the human sense of endurance in a universe that often seems indifferent. The endurance of photons in the presence of a neutron star is not only a triumph of nature, but a triumph of perspective. For us, light is the only bridge to such distant and hostile realms. No spacecraft can land on a neutron star, no probe can survive its gravity, no human eye can look upon its surface. Yet photons bring it to us. They cross thousands of years, unaffected by the passage of time, carrying intact the story of where they began. By studying them, we share in that survival. Light tells us that gravity bends space but does not always silence it. The bending is severe, wrapping photons from hidden sides of the star into our line of sight. But those distortions become maps of curvature. Light tells us that magnetism twists the vacuum, but does not annihilate radiation. Polarization patterns reveal the unimaginable fields that shape the star. Light tells us that atmospheres scatter and absorb, yet still transmit bursts that reveal nuclear fire on the surface. Each obstacle becomes not the end of light, but a filter, one more layer of meaning carried outward. This survival resonates beyond physics. It mirrors our own search for meaning in difficulty, our own endurance in the face of crushing pressures. Just as photons emerge altered but present, we too carry scars of struggle, but remain voices in the dark. The neutron star does not know it teaches this lesson, but it does. Through the persistence of the light, it cannot fully trap. Astronomers have come to rely on this persistence, not as a marvel, but as a tool. They measure the timing of pulses to detect gravitational waves, use bursts to measure distances, analyze spectra to infer the nature of matter under densities higher than any experiment can reach. The photons are practical, not poetic, but their survival makes both possible. They turn collapse into science and endurance into knowledge. And yet, the poetry is unavoidable. To see a pulsar's rhythm is to hear time itself kept by a dead star. To watch a magnetar's flare is to glimpse light breaking free of storms fierce enough to alter our planet's atmosphere. To measure redshift in a neutron star's spectrum is to confirm that gravity leaves fingerprints, even on the photon. These are not only data points, but reminders of the scale of the cosmos, of how far light can travel, and of how much it can endure. The triumph of light is not absolute. We know there is a boundary where photons cannot win, the horizon of a black hole. But neutron stars remind us that survival persists even in the face of overwhelming odds. They are the last defiance before silence, the last stars whose light reaches us from the edge of collapse. That defiance is what makes them precious. They allow us to see what lies just short of finality, to study the laws of physics where they nearly break. As this part ends, the triumph of light is clearer. It is the resilience of photons, the survival of signals, the endurance of messengers across distances beyond human scale. It is also the triumph of human ingenuity, building instruments to catch them, decode them, and turn them into knowledge. In the next and final section, we will bring these threads together, closing with the image of light as both physical survival and enduring symbol, a reminder that even under the heaviest burdens, something escapes, something endures, something shines. Light has carried us from the collapse of stars to the edge of silence. We have followed photons as they climbed from neutron star surfaces, as they pulsed in lighthouses of magnetized beams, as they twisted through magnetic storms, as they threaded fragile atmospheres, and as they traveled across thousands of years to reach us. Each stage has revealed the same truth. Light endures. In neutron stars, gravity nearly wins. It bends photons into arcs, it slows time, it stretches wavelengths into redder bands, yet it does not erase them. Instead, it leaves signatures, marks that we can read. The redshift of a spectral line, the bending of a beam, the distortion of an image, all are scars of the battle between gravity and photons, and all are messages that reach us still. In pulsars, light organizes itself into rhythm. It becomes a clock, steady across eons, its beat unbroken by collapse. In magnetars, light survives storms fierce enough to alter Earth's own ionosphere, carrying the memory of crustquakes across galaxies. In atmospheres, photons survive scattering and absorption, emerging changed but still carrying the truth of fusion and density. In every case, gravity and magnetism press, but light persists. The triumph is not only physical but symbolic. In the darkest environments, where collapse has crushed matter into near silence, photons still escape. They are whispers against overwhelming force. Voices that say, "This star lived, this star collapsed, this star endures in light." The lesson is profound. Even at the brink of silence, survival remains possible. Even under the heaviest of weights, something escapes to tell the story. For humanity, this triumph is also a gift. We build instruments to catch the photons, to decode their stories, to turn them into knowledge. Without them, neutron stars would remain abstract mysteries. With them, we measure densities, radii, masses, and magnetic fields. We test relativity, probe nuclear matter, and chart the edges of collapse. The triumph of light becomes the triumph of understanding, of knowledge born from survival. And so, the book ends where it began, with light escaping. From the fire of a supernova to the silence of a black hole's horizon, light is the messenger. It endures nearly everything, altered but alive. And when it reaches us, it carries truth across impossible distances. Its resilience mirrors our own. Our drive to endure, to resist silence, to carry meaning across time. On a neutron star, gravity presses with unimaginable force. Yet light still breaks free, a whisper of resistance, carrying the story of a star's death across the universe.